Linear regression. Linear regression, one of the most fundamental algorithms in machine learning and statistics. Linear regression models the relationship between an independent variable and a dependent variable by fitting a straight line. This line, defined by a slope and an intercept, represents how changes in the input affect the output. The goal is to minimize the difference between predicted values and actual values, usually done by minimizing the sum of squared errors. This results in the best fitting line through the data points. Linear regression is easy to implement, interpret, and computationally efficient, making it ideal for establishing baseline models and understanding data trends. It's widely used in finance, economics, biology, and many other fields to predict continuous outcomes such as prices, growth rates, or risks. Logistic regression. Logistic regression, a classic in machine learning and a go-to for binary classification. Don't be tricked by the name. It's not for regression, but for predicting categories like yes or no, spam or not spam. Picture this. You're guessing if it'll rain based on temperature and wind. Logistic regression takes those inputs, blends them with weights, and uses the sigmoid function, a special curve, to turn them into a probability between 0 and 1. Above 0.5, it's yes. Below, it's no. Simple. It draws a boundary to split two groups and learns by tweaking weights with maximum likelihood estimation, maximizing the chance of being right. It's fast, interpretable, and perfect for linear relationships, like medical diagnosis or fraud detection. But if your data's too curvy or complex, it might not keep up. So, logistic regression is straightforward, powerful, and a solid foundation for classifying binary outcomes. Decision trees, a powerful and intuitive machine learning technique for classification and regression tasks. At their core, decision trees operate by recursively splitting data based on feature values to form a tree-like model of decisions. Each internal node represents a test on a feature, each branch corresponds to an outcome of that test, and each leaf node holds a prediction. Imagine a decision tree as a wise guide navigating through a forest of data. At every fork, it chooses the most informative path, gradually homing in on the right decision. By following this path from root to leaf, the model builds a clear and interpretable logic that mirrors human decision-making. As a result, decision trees provide both accurate predictions and transparent reasoning. This makes them invaluable in domains where explainability is crucial, such as finance, healthcare, and legal systems. Advanced variants, such as random forests, gradient-boosted trees, and extremely randomized trees, expand the basic concept by combining multiple trees. These ensemble methods reduce overfitting, increase generalization, and significantly boost performance across complex datasets. Decision trees transform data into hierarchical decision structures, enabling not just prediction, but deep insight into the factors driving those predictions. Random forest. Random forests, a powerful machine learning technique for robust prediction and classification. A random forest is an ensemble of decision trees, each trained on random chunks of data and features, working together to make a final call. This process harnesses the wisdom of the crowd, smoothing out individual errors to boost accuracy. Imagine each tree as a voter, casting its opinion on whether an email is spam or not. Then the forest tallies the votes or averages predictions to deliver a strong, unified answer. As a result, it not only handles complex patterns, but also resists overfitting better than a single tree. This strength powers applications like fraud detection, medical diagnosis, and stock prediction. Advanced tweaks, like tuning tree depth, number of trees, or feature sampling, push its performance even further. They ensure diversity among trees and balance speed with precision. Random forests transform data through collective decision-making and open new frontiers in reliable, high-accuracy modeling. Gradient boosting machines. Gradient boosting machines, or GBM, a top-tier method in machine learning. Imagine you're building a team of weak players, simple decision trees, that together become a champion. GBM does this by adding trees one by one, each fixing the mistakes of the last. It's like learning from your errors step by step. It uses a process called gradient descent to minimize a loss function. Think of it as tweaking predictions to get closer to the truth. Start with a basic guess, then let each new tree focus on what's still wrong. It's great for both classification, like predicting yes or no, and regression, like guessing a number. You control it with settings like the number of trees, learning rate, how big each step is, and tree depth. A small learning rate with more trees often wins, but takes time. GBM excels with messy data, but watch out. It can overfit if you push it too hard. Support vector machines, or SVM, a powerful and versatile algorithm used for classification, regression, and outlier detection. SVM works by finding the optimal hyperplane that best separates data points of different classes. This hyperplane maximizes the margin, the distance between the closest points of each class, known as support vectors. In cases where the data is not linearly separable, SVM uses a technique called the kernel trick. Kernels transform the data into higher dimensions, allowing SVM to find a linear boundary in a non-linear space. SVM is effective in high-dimensional spaces and works well, even when the number of features exceeds the number of samples. It's also resistant to overfitting, especially when properly tuned. It's widely applied in text classification, image recognition, bioinformatics, and financial modeling, wherever high accuracy and robust decision boundaries are needed. ARIMA, or time series models. ARIMA, a powerful model for time series forecasting. ARIMA stands for Autoregressive Integrated Moving Average, is a versatile statistical model designed to analyze and forecast data points collected over time. It combines three essential components: autoregression, differencing, and moving average. In autoregression, the model uses past values to predict future trends. Differencing helps to stabilize the time series by removing trends or seasonality, making the data stationary. The moving average component smooths out short-term fluctuations by modeling the error term as a linear combination of error terms from previous time steps. Together, these components enable ARIMA to capture various patterns in time series data, providing accurate forecasts. This model is widely used in fields such as finance, economics, and weather forecasting, where understanding past trends is essential to predicting future outcomes. In short, ARIMA models offer a robust framework for time series analysis, transforming historical data into reliable forecasts. Bayesian networks. Bayesian networks, a powerful tool for reasoning under uncertainty. Bayesian networks are probabilistic graphical models that represent a set of variables and their conditional dependencies using a directed acyclic graph. Each node represents a random variable, and each edge denotes a conditional dependency between variables. The strength of Bayesian networks lies in their ability to model complex relationships and update beliefs as new evidence is introduced. This makes them highly effective for decision-making, diagnostics, and prediction in uncertain environments. Using Bayes' theorem, the network can infer the likelihood of outcomes based on prior knowledge and observed data. They are widely used in areas such as medical diagnosis, risk assessment, natural language processing, and AI systems. Bayesian networks offer a structured, intuitive approach to modeling uncertainty and making informed predictions based on probability. A revolutionary deep learning technique for efficient data compression and reconstruction. At its core, an autoencoder is a specialized neural network designed to encode input data into a condensed latent representation, and then decode it back to its original form. This process forces the network to extract and retain only the most essential features of the data. Imagine the encoder as an artist who distills a complex image into its fundamental elements. Then the decoder meticulously reconstructs the full picture from this compressed information. As a result, the model not only compresses the data but also learns its intrinsic patterns. This capability enables robust applications such as anomaly detection, image denoising, and generative modeling. Advanced variants such as variational autoencoders, sparse autoencoders, and convolutional autoencoders extend this concept further. They are designed to generate new data samples, impose sparsity and feature selection, and capture spatial hierarchies in visual content.